السلام عليكم ورحمة الله وبركاته.
وعليكم
السلام
السلام.
عليكم. Can you hear me?
Yes, doctor.
Can you hear me? Because it tells me that my mic has a problem.
Yes, we can.
Can somebody say something? All right. Can you hear me? Please write. We can hear you. I don't know what happened this time. Okay, thank you very much. Because my mic, in the corner there, the mic icon is not always coming. It comes and goes. Even the speakers. What happened to this computer? Somebody must have cast a spell. You know the spell, magic spell. This is all right. We will remove all the background noise so no one will hear it. Okay, good, good. I think I cannot hear you guys. So you probably, because I cannot hear the change of level in the speaker, supposed to hear it. This is the first time. As long as you can hear me, this is the most important. I don't need to hear you. Okay, so let's see, we have 1, 2, 3, 4, 5, 6, 7, 8, 9. Is it only 9? Okay, let me check again there. The participants. Computer is very slow today. Very slow. What happened to it? Okay, I see, mashallah, mashallah. Most of you are there already. Good, good, alhamdulillah. Okay, so let's just go ahead straight and share the material. We have finished 3 chapters. Your quiz has been postponed for 1 week, almost 1 week, I think. I changed it yesterday for 1 week, which was what, 7 days later. So please check the date. Okay, now this is, remove that participants panel. Share. Usually I like to hear at least somebody's voice. Umar, how are you, Umar? Something is not right with the computer. It's much slower than previously. Hey guys, can you see this chapter 4, storage devices?
Yes.
I usually get some echo. Oh, mashallah, Omar finally heard me. I'm Omar, the developer. Mashallah. Okay, thank you very much. I feel it feels like I'm talking to some quiet, hollow thing. I mean, the field. Usually there is normally you will be given some feedback with little noise so that you know that you are dealing with, you are communicating with somebody. Anyway, okay, so we have 2 chapters to finish today. I will commit some things for you to go to read, as usual, because this, this information overload is very difficult. For the last, 20 plus years, information over, especially when the internet came about, especially now after the AI, because information is a lot there, even every little thing in these chapters even. Sometimes I go to ChatGPT, ask, give me more about this, give me examples, it's so many things. So anyway, we're talking about the fundamentals here. If you want to have any up-to-date information, of course, you need to dig further. Okay, storage devices, we're talking about computer organization architecture. Storage devices for the computer. Computers, of course, the information that is being communicated, being handled, has to be saved somewhere, whether temporarily or permanently. Temporarily, it is saved in the memory. Permanently, it is saved in the usually external storage. That is the permanent storage. That is the non-volatile. Okay, so we need to store data permanently. So we call it external, secondary, or auxiliary. Wow, why do they come with all these names? Auxiliary means additional, extra storage. Okay, so we have the magnetic tape, we have the magnetic disk, which is the hard disk. We have the optical disk, which is the CD-ROM or DVD-ROM. Remember DVD-ROM that was there? I think Omar is old enough, maybe you remember that, the developer. So DVD-ROM yesterday, I was searching something at home and I saw a bundle of DVDs. I used to buy them by the 50 together, DVD read-write. Initially, they just came out as DVD read, so you can write it once the first time. Once it's written, you cannot write to it again. Then you can read write, and then the USB came, and all hell broke loose, as they say. USB came to as a disrupting technology. Okay, we will not talk about USB here. We talked about it, I think, last time. Okay, so for large capacity, costless, we use the hard disk drive. Also, we use the not the user, the customer, but the big companies, big corporations, they use the magnetic film. Okay, magnetic film, a roll just like the cassette tape. If you have seen it, if you are old enough to remember the cassette tape player, that was the film which, rotates. They have this type of film, but like 1,000 meter long in, disc pack. I've seen it. I've seen this in the universities. Where they have mainframe, they need the large storage capability. They have these magnetic films for backup, usually for backup, for storage for a long time, because it is very high quality and it can last very long time. The hard disk, they can last 5 to 10 years, hard disks. They say 3 to 5, 5 to 10, also depends on how often you use it, but if you use it, not very frequently, on and off, but you use it every few days, few weeks. So don't leave it, to corrode, the stuff inside of it, or to be affected with humidity. It can last, I think it said, up to tens of years, but you have to be very careful how to use it. Anyway, back to storage. So the data that is being processed must be copied, must be saved somewhere. Okay. Oh, okay. See. So the data to be processed must be saved temporarily in the internal storage. We know that we have to load the data into the memory, then the CPU will be working on it. Okay, also the CPU itself has its own memory inside, which we call registers. All right, so we have, we will look at the storage structure, disk structure, caching very little at the very end. Okay, and then summary. Summary is always very good. Please make it a point to, after you have read the material, you go to the summary and read it. It will refresh. It will remind you of what you have read. Okay. So guys, if you for some reason you cannot hear me, let me know. Okay, let me know by writing in the chat more than one. Because I don't know, I cannot hear anything. I think somebody tried to answer, but I couldn't hear, and it said my speaker. Anyway, okay, so At the end of this, we'll take a look at all of these things, okay? The different storage devices and internal storage, direct access storage, and serial access storage. Serial access is the film because you have to roll it, so it goes serially. Direct access, you go straight to the track or the sector that you want to read the data from, which is what is being done. Also for the SSD as well, solid state devices, memory, it's electronic, so you do not have to go through the reel, to rotate it. Then look at some properties, CD-ROMs, redundant array of independent disks, RAID, RAID, redundant array of independent disks. We have 7 levels, actually more than 7. We'll look at them also. I have some additional information for you to go through. That uses disk stripping, which is distributing the data onto multiple disks. Actually, just like what the hard disk does. Okay, then fault tolerance, it's a bit data caching. Okay, now we have this some terminology. DSD, direct access storage device, and then we have serial access storage device. Direct access goes straight to it like the hard disk. Serial access is like the film, magnetic film. Then okay, within the hard disk we have okay, sectors, not here, sector, we know the sector. Then we have a track, sectors make tracks, sectors, several sectors make clusters. So a group of contiguous sectors within the hard disk, they are called clusters. Then one full round is called a track. There are so many tracks on the palette, and all these tracks for top track, and then the next palette, they have the next track. All these tracks on top of one another, they make up a cylinder. So a cylinder is a set of tracks on the magnetic disk that are directly above and below each other. We'll see a picture of it. We have the SSD solid state device. We have the constant angular velocity, CAV, for the speed of magnetic disk, because the disk has to rotate and the read arm will have to go in and out. So this will rotate and this will go to the proper position to read from the track or from the sector on the track. The speed of accessing is called constant angular velocity. Actually, this is the rotation speed. Then we have the constant linear velocity. This is for rotated speed of optical disk drive. The optical disk also must be rotating, right? So that we can, the read laser read head for this optical disk, because optical means it uses laser, can reach, the proper sector to read from. Then we have the redundant array of independent disks, RAID, which is a kind of external storage consisting of usually 2 or more devices, drives. Fault tolerance, you tolerate a fault, means you can recover from unexpected hardware or software failure. Recover from an unexpected hardware or software failure. Something fails, to recover from it, then shows how tolerant the device is. Okay, this is done in RAIDs. Okay, RAIDs are done basically for this kind of fault tolerance. When some disk, some device, it has one bit fails, it will be able to reconstruct the bit that was missing because of, the failing device, because that's why we have several devices. It consists of 1 or more drives. Each drive will have 1 bit. So we have several drives. Okay, the bits will be divided between them, but some of them are several actually. So when the bit is missing, we can use the parity to identify what is the missing bit, what it was. Sometimes you will have also double parity. Disk stripping, meaning spreading the data over multiple disks. Disk mirroring means replicating or duplicating the disk, so that the one disk has the data, another disk also has the similar data exactly. This is RAID 1. Then we have disk cache. We know the cache is temporary storage, right? Cache is temporary storage. So data stores data or program that is needed soon in memory chips. Okay, disk cache, the hard disk, we know the hard disk itself has a chip in it that stores the data that has been accessed. so that if it is needed again, it can get it from this integrated circuit, which is very quick, instead of having to go to the hard disk and then it will rotate and then access that again. So this cache is to make it quick, fast to get the data. So to avoid having to retrieve the data from the hard drive when they are requested again. Memory used for this disk can be either a portion of RAM or memory chip located inside the hard disk. Normally now we have almost all hard disks have hard disk cache within it. It can be like 8 kilobyte, the more the better, but it's too expensive. 8 kilobyte, 120 kilobyte, whatever, so usually I remember the numbers, 8, 32, 64K, right. All right, storage structure, okay, we talked about the direct access storage device, say serial or sequential. I said serial or sequential, it's the same thing, because it's in series. All right, now the magnetic hard disk. Magnetic disk is the hard disk. The hard disk is the most famous for saving data. Do you know how the hard disk looks like? It's just like a box. I think we saw it in lecture 1 or 2, right? The hard disk. It's just a box. Imagine this phone, okay? It's slightly wider and thicker. Okay, we have half height, we have full height. Full height will be like 3 inch, half height will be 2 inch. Okay, so now this hard disk consists of, let's go to the drawing. This is how the hard disk looks from inside. This is how it looks from inside. It has the platter, okay, I said platter, or disk, actually. That's why they call it hard disk. So platter, just like a disk, basically. Then we have, this is the top view from on top of the disk or the platter. This is a sector. How many sectors per track? One full round cycle there is a track. So this is one track, this is another track, this is a third track. Okay? So, okay, they're pointing to the line. It depends on how wide they are. So there can be thousands of tracks. Also, there can be hundreds of sectors within one track. All right, so this is how it is identified. So these tracks they contain the same amount of data. So this track contains the same amount of data there. Okay, sector is a small one. Track is the complete lap, if you like. Okay, so this is the read-write arm, this one from top and bottom. So they are both, we have usually it was like top only, and then they became both sides because they want to conserve space. So we have read-write head from both sides. This is the spindle, the center around which those disks rotate. So we have, this is one track, another track below it, another track below it. All these tracks together, all of these tracks together are called cylinder. So there are number of cylinders, same as number of tracks. So if, for instance, here, let's say we have 1, 2, 3, 4, 5, 6, 7 tracks, means we have 7 cylinders. Because each track will consist of, from each disk or platter, has the same number of tracks. The topmost track together, they make up the topmost cylinder, then inner cylinder, then inner until the innermost cylinder. Okay, so this is how the hard disk looks like. So please read this material here. Okay, so concentric circles called track. Concentric means round circles. They rotate around the center. Okay, so track 0 is the outermost. The one outside is called track 0. Then next will be track 2, track 3, until it reaches track. The last one will be at the core of the circle, at the origin of the circle. Okay, so we said each one has an address. Each sector has an address. Cluster is the number of sectors. Contiguous meaning one after the other. Okay, so if to access only the whole sector has to be read. The whole sector, if you want only just little piece of information, the whole sector will have to be read, and the data is written as words, one full word. Okay, even if we need to write only 1 byte, the disk will write the entire sector. Also, if we want to read 1 byte from the sector, the whole sector will be read. That's why this also can be saved in the cache. So if you need to read the next byte, it is already in the cache. Okay, so most systems have fixed length of 512 bytes per sector. Okay, so one sector will contain 512 bytes. All right, so sectors are fixed length. All right, each one has a unique number, which is consisting of the surface number, if it is top for double side, then the track number and the sector number. Remember, we have them all in one cylinder. Okay, it doesn't say here, but I'm not sure if the data is like 1 bit per sector or more than that. We need to dig into that. Okay, because normally when you have 8 memory chips, the data to be written to these memory chips will be 1 bit per chip, so that when you read 1 bit from each chip all at once in parallel, so that the reading will be done in parallel instead of reading sequentially. You just read it one time, 8 bits. Okay, so guys, are you with me? Because I hear, you say vacuum, I hear silence. How does a silence sound like? Silence. Okay, thank you very much. Thank you for the quick response. I appreciate it. Okay. All right. So this is about the hard disk still. Estimating the capacity. Okay, capacity, I think you should know this by heart. I mentioned this before. I've mentioned it in the digital system. You need to know this by heart. Kilo is 2 to the power 10, which is 1024. Mega is 2 to the power 20. Giga 2 to the power 30. Tera is 2 to the power 40. Tera of anything, terabyte or terabit will be 2 to the power 40, byte or bit. Beta 2 to the power 50. Exa 2 to the power 60. Zeta to the power 70. Iota 2 to the power 80. What comes after that? I don't know. We never had to go there. Imagine to multiply by itself 80 times. 2, 4, 8, 16, 32, 80 times. What will the last number be? Oh my God. Okay, so this shows the capacity, how large the bits, because we go in ones and zeros. So it shows the capacity. These are the names that we use: gigabyte, terabyte, petabyte. I think petabyte, we use petabyte when even exabyte when we're talking about the supercomputers. Zettabyte and yottabyte, I don't know. I mean, are they used? Definitely they are used. Of course, like the data that you want to save, the large size of data will be in zeta and yotta. The magnetic film, they contain data, historical data, and they save this data. One of the places that they save them underground in the is it in Antarctica, and some countries they save the data for the humanity, so that centuries later when something happens, somebody will come and then they will discover the data, they will know what was happening. But it's good that someone can get hold of all of this data. Okay, so capacity of track cylinder and drives is given by, okay, capacity is basically how many bytes per sector, how many sectors per track, how many tracks, then how many cylinders, right? So example, this is example of some numbers here. You have a file of 50,000, okay, a file with 50,000 fixed length data records. So 50,000 records. Each record is 256 bytes. How many cylinders does it need? Because we need to find the capacity of the cylinder. So which means we have, okay, this given here, bytes per sector, 512 bytes per sector, 63 sectors per track, 16 tracks per cylinder, the tracks on top of one another. Okay, so this gives us the cylinder capacity, which is 512 times 63 times 16. 512 times 63 times 16, which is 516,000 something bytes. So this one, 50,000 record multiplied by 256 bytes gives us 12,800,000 bytes. How many cylinders do we need? Then you divide that by the capacity of the cylinder, gives us 24.8 cylinder, which is 25 cylinders are needed. How many cylinders are there? We have 4096. So we only need 25 cylinders, basically, for this file of 50,000 records, where each record consists of 256 bytes. Okay. Then he talks about constant angular velocity. Okay. Rotating disk at fixed speed, constant angular velocity. All right. Okay. It's good to read this. Same number of sectors in the inner track as the outer track, same number of sectors. Okay, so amount of bits in the outer track should be the same, which means because outer track is larger, so the density of information there will be sparse compared to the compact density of data in the inner track, closer to the center. Anyway, we don't have to worry about that. Okay, so space between bits outside will be more than those inside. Okay, just some physical attributions or specifications, properties, description. Okay, so advantage of using CAV, which is constant angular velocity, is the disk spin by the same speed for all positions, so that you have our sector, all sectors on the same line. So this, when it speeds, the arm will go straight while that is speeding. Okay, so for fast access data, disadvantage of this constant angular velocity. Angular means round, all right, like an angle. The angle is expanding when it rotates, like 360 degrees. Okay, that the amount of data that can be stored on the long outer tracks is the same as the ones in the short inner tracks. This one disadvantage. But because we have constant angular velocity, it makes it fast access. The storage capacity is wasted on the outer tracks because the density of data there is less than the ones inside. Well, this is technology, this is physics. You cannot have everything everywhere all the time, every place. There has to be some advantages and disadvantages. This is how life is. You give and take. It's never perfect. Yeah, this access time is the rotation speed versus the speed of the arm going in and out to the proper sector. Okay, so the arm going in and out is called the seek time. Okay, seek time. All right, where is it? I think I was skipped it. Okay, the time it required to move the disk arm, which has the read-write head, okay, from both sides in and up, I mean down and up, to the desired track is called the seek time, so that it goes to the proper track. And the rotation, this constant angular rotation or velocity will rotate so that the proper sector comes under this arm. So it goes in and out with this, rotates so the proper sector comes there, and then while it's rotating, it will read. But it reads from all the cylinders, all the platters at the same time. So the sum of the time for all possible seeks. Okay, then we come up with the average access time. All right, because to access different sectors will take different time. The slowest thing is the movement of this read arm. This is the slowest because rotating is very fast. Rotating can be up to mostly 7,600 rotations per second, RPM, per minute, RPM per minute. Okay, 7,600 per minute. There's 5,400 also, which is the slower one, like for laptops. For desktop PC, it's faster. Of course, this is if you are using a hard disk. Also, there are, I have seen fast that go up to 12,400 or 12,400, something like that, RPM. Okay, so transfer rate is the rate at which data is read from or written to the disk. The total amount of time is the sum of the seek time, movement of the arm in and out, rotational delay, which is to rotate the proper sector under the arm, and transfer time. All together, they make the access time for read and write. Of course, access time for read is faster than access time for write, because for write you have to do some some operation, some to magnetization and whatever, they do in there, the physics of it. So reading is always faster than writing. So normally it's between 80 to 160 megabyte per second. Okay. Now, then the hard drive interface can be parallel or serial. Now, mostly they are SATA, which is serial ATA, which is advanced technology attachment, SATA, which is a smaller ribbon cable. Previously, the parallel ATA used to be very wide, I think 36 lines. This ATA, I don't know how many lines, maybe 16 or even less, probably. If you open your hard disk, I mean your main unit of the computer or the desktop, you can see usually it's a blue ribbon, blue wide cable called SATA. Sometimes blue, sometimes pink, sometimes yellow, sometimes red. Okay. So magnetic disks are either hard disk or floppy disk. Oh, okay. We're talking about the hard disk so far. What about the floppy disk? Have you ever seen a floppy disk? Muad, maybe you have seen a floppy disk. Mr. Muad, is Muad here? Yes, I think so. Sometimes I mix, which lecture has which students, because some students are different in more than one lecture. The floppy disk used to be about what, 7-something inch. My time, I've seen that for text specific software that uses this very big floppy disk. My time, I started using PC, it was using 5¼ inch. Then it went to 3½ inch. Then boom, they just disappeared, not used anymore. I think the last thing, the internet, the browser software, I remember, came with about 14 3½ inch disks, floppy disks, I remember. And that was only, not everybody can use, only the officials. Okay, so now we have the SSD. Okay, floppy disk is no more. If you want to, you can read about it, but it's no more. Have been obsolete. Now we have the memory devices, which are high density, high performance memories using EEPROM, which is the SSD. SSD uses the technology of EEPROM, electrically erasable and programmable read-only memory. You know this already, right? There is an idea of having exams by talking to the students face to face. Really, there's this idea, which is the proper way to make sure that the students really study and learn and understand and can explain, instead of just writing or typing one way or another. Okay. Now, solid state drives, SSD, which is the integrated, consists of integrated circuits, basically flash chips or flash drives. Solid state drive consists of flash integrated ICs using the EEPROM technology, electrically erasable and programmable, except that the flash drive is written and erased in blocks, not by one byte. Yeah, the speed is about 550 megabyte per second, compared to, see, hard disk up to 160 megabyte per second. So these are almost at the same time. So the flash drive is about more than 3 times faster, 3-4 times, even faster, much faster than that. More reliable, requires also much less power, because to rotate something takes more power. Okay, so it's retrieved, data is retrieved electronically directly. Optical disk is the DVD. If you have seen DVDs are the optical disc, or we call them CD-ROM or DVD-ROM. DVD is digital video. This previously used to be called compact disc ROM, compact disc. Okay, read-only memory. It used to be only R, which means you can read from it. You write only once, and then you can read only. Then CDR, then came the CDRW, read, write. You can read and write from it, but only limited number of times because of the technology. Now the technology with the flash drive, you can read and write from it millions of times. So the flash drive can last tens of years. All right, read about the flash drive. It's very interesting. Okay, ask ChatGPT. So the flash ROM, they are high density storage devices. The CDR, okay, used to be about 540 megabyte or 0.54 gigabyte. The DVD was 4.7 gigabyte, around that, 4.7 gigabyte. This was 5.4, 540 megabyte. Okay, so CD-ROM, it uses laser because it's optical disk. We call it optical disk. This is optical, okay? Optical disk uses laser, the read head, read and write, uses laser beam. So it either applies laser and cause pit or land. Land means nothing done. Pit means it will make a, how do you call it? A pit, like small hole. So the change from zero, from no hole to hole is 1. From hole to no hole is also 1. Otherwise, if there's no change, it is 0. The data is 0. This is same as AMI, which is alternate mark alternate mark inversion, if you remember, in the datacom. Anyone taking datacom? This is same as AMI. For one you go down, next time you go up, next time you go down, next time you go up, right? This is AMI. That was not in the exam. It was Manchester code. You know, these codes, when you work with them, you know them very well, inshallah. Okay, so this is how the data is written on the surface of the disk. No possible to have two adjacent ones. Okay, one together. You cannot, because must have 0 and then back to 1. So then we have to do some kind of encoding. Encoding, they use the 8 to 14 modulation, one type of encoding, the EFM, 8 to 14 modulation. Okay, so from 8-bit we make 14 bits, so that if we have two consecutive ones, then the ones will be spaced apart. Okay, so that we can identify where the one is going down to up or up to down. All right, so this is encoding scheme, EFM, 8 to 15 modulation. Okay, these they have single spiral track because it's only one side. Is there double side CD DVD ROM? Is there double side? I don't remember. One side is the shining side. The other usually comes with some writing or whatever. Okay, so this has what we call constant linear velocity. Also, again, this also rotates, and the read head also goes in and out, but that is laser one. This works in concentric, not concentric. They call it, I think concentric. Concentric was the hardest. This one is, what's the word for it? It starts from the inside and then spiral all the way out. One continuous track throughout the whole thing. One track, instead of having one track, second track, third track, like the hard disk, this has only one track from the middle and then spiraling outward. Okay, so this has beginning near the center, spiraling out to the outer edge. Track is about to equal length sectors, so each sector is the same length. Sector near the outer edge has the same amount of space as the sector near the center of the disk. All right, so outer part of the track has much more information than the inner part of the track. Now, I think some writing there is not right. Anyway, so this is how it looks, one continuous track. Also, it has constant linear velocity of rotation. Okay, this has to be adjusted so that when it goes to read from the inside, it has to be fast because the data is close together. Outside, it has to be slowing down because actual rotation speed. The rotation speed outside is faster than inside, so the speed has to be adjusted. Okay, so this is removable, which means you can have so many of it, while the hard disk is limited. Whatever space you have there is, that's it. But for the DVD or CD-ROM, you can have as many as you want. I used to buy them in 50. In the beginning, one DVD, one CD actually used to be about 5 ringgit. Then when about 50 DVDs, the price was about 20 ringgit. So I mean, of course, that was after many months when it became more famous, more widespread. Disadvantage of CD-ROM is that it's poor seeking performance. Okay, seek meaning to read, because it has to slow down and speed up, while the hard disk is the same speed. This compares between the CD-ROM and magnetic disk. All right, so please Okay, go over it. It's the thing that I have mentioned. One spiral track for CD-ROM will have concentric tracks, many tracks. Sector length, same length here. Also, their outer length is the same. Okay, different lengths for magnetic disk. Or talking about sector. Sector is the same. The track is different. Okay, bit density outside is less density, while this one has the same density for CD-ROM. Amount of data per track. Inner part has smaller amount of data. Amount of data is the same for magnetic disk, both of them. Advantage, this one has storage space available throughout the disk. This one has some data that, because the density of the data outside is sparse, not very high, so it loses some storage space, but it has good seek performance. The basically information transfer rate, right? Disadvantage is the change or rotation speed has to be done, which causes poor seek. Actually, everything, as I mentioned, has its advantages and disadvantages. So you have to just use the thing, the best way that it is to be used for. Okay. Again, capacity addressing for the DVD, second of playing 1 second, it goes by time. 1 second, because it will like 1 hour. 1 second has divided to 75 sectors. Each sector is 2 kilobytes of data. So we have 1 hour CD. Okay, so 1 hour means 60 minutes times 60 seconds times 75 sectors per second times 2 kilobytes per sector, which is 540,000 kilobytes, which or 540 megabytes, right? Almost. Even though when we talk about K, that's 1024. When we say mega, that's 1024 times 1024. So mega is not like million, it's more than million, a little bit. So million with little less than 100,000. Okay, sector is addressed by minute, second, sector. So minute, second, sector to specify the sector that is to be read from. Then we have serial access, magnetic tape. Magnetic tape, as I mentioned, is the reel, I call it reel, which is the spool actually, okay, or bakara, if you like. There's no direct access. You have to turn the magnetic tape to reach the proper location. Okay, but this is famous actually. It is very good use. It's very fast sequential access to data, because normally this is used for bulk, a lot of data to be saved. You don't use this for every day. All right, it's not to be used for everyday work. So very fast sequential access. This compact, suitable for different environmental conditions, easy to store and transport, and cheaper than magnetic disk because of its large capacity. All right. So nowadays it is mostly used for backup and data archiving. You store your data for a longer time, archiving. So the 9-track, we used to have this one in our car last time. You know, we call it 9. They just call it 9-track. It's just like cassette, but it's slightly bigger, almost as big as this, even thicker and little higher. I mean, the height of it. 9-track because it has 8 tracks for data and 1 track for bits. So it has 9 tracks of data. All right. So this is data bulk between every data block. Between every data block and the next, there is some gap, consists of all zeros. Okay. So this is the 9-track or magnetic tape. I thought this is extinct. I thought it was already extinct, but when I asked ChatGPT, no, it is there, of course, but for archiving purposes. It is not to be used every day. Okay, I think I just was waiting for something. Okie doke. All right. Sorry, guys. Just a second, please. All right. So this is the 9-track. Is it 8-track or 9-track? We used to call it 8-track, 9-track. I think 8-track. I remember it was 8-track. So maybe 7 bits plus parity. This one is 8 bits plus parity, the most famous one, according to this writer. This is from the William Stallings' book. Okay, so the frame consists of 8 bits plus parity bit, right? So performance of the tape drive is measured by tape density, how many bits per inch per track. Also tape speed, how many inches per second rotation, and the size of interblock gaps, the gaps, how big is it? 0.3 inch or 0.75 inch, right? Also this table summarizes the difference between magnetic tape, magnetic disk direct, magnetic disk and CD-ROM. This sequential access, magnetic tape, and magnetic disk and CD-ROM are direct access. This pyramid doesn't show this stuff inside, but it's written out here actually. This is magnetic tape, optical disk, hard disk, internal memory, and registers. We have seen this. Where did we see this last time? We saw it somewhere. So when we go up, it becomes more expensive. Go down, becomes cheaper. Also, when we go up, it becomes a smaller capacity, the size of data that it can take. Go down, it becomes larger capacity, but the cost also go up, it becomes more expensive. Go down, becomes less expensive. Go up, becomes faster access time. That's why it is more expensive and less data. Go down, it becomes slower access time. Okay, so this is the storage hierarchy. If you look at the storage hierarchy on the internet, I think you can find it done properly. If someone reminds me, then I can also search for it, and or maybe some of you can search for it and then share it on the WhatsApp group. Okay. So now, okay. Now the disk structure. All right. We said we have fault tolerance. Because of fault tolerance, actually, you must use disk drive for storing data and programs. The disk may crash. When the disk crashes, it's bye-bye. Actually, there are companies that can still retrieve data from the crashed hard disk. Okay, but it will cost you a lot. And also you have a lot of information that is private. You know, when the hard disk crashes, okay, you just put it aside. You don't take it to a company to retrieve data from it, because you have all your information there. They will have access to all your information. So I have a few hard disks at home, just in the storage for almost what, 30 years, let me see, 40 years, more than that, from the 90s, almost 30 years. Well, I just keep it. You know, if it crashes or don't use anymore, but you don't throw it out, because someone finds it, then they can have access to information. Just like when you lose your USB drive. Oh my God, USB drive, if you have a lot of things on it, and then someone finds it, very difficult. Okay, so we have to have something that is fault tolerant. Fault tolerant means you have to have some kind of mechanism to have additional availability of the data. That's why I have redundant. Redundant means more one copy. Okay, when you have redundancy means you have 2 or 3 copies of the same thing. That means you have redundancy. That's why they came up with this RAID, which is redundant access independent disks array, redundant array of independent disks, basically disks. They have levels of this disk array. They have levels, level 0, 1, 2, 3, 4, 5, 10, 20, 50, 60, as we will see. 50 is 5 plus 0, 66 plus 0. We have 10, 1 plus 0. So we have RAID level 0. RAID level 0, basically you have at least 2 disks. So the data will be split into what we call data striping, or distributed on them. So first bit, second bit, third bit, fourth bit, and so forth. Okay, this is not fault tolerant. All right, so data spread improves overall I/O performance because it's faster to retrieve 2 bits at a time, but then not fault tolerance, because if one drive fails, you lost the data. Actually, this is part of a better solution, okay, which is what we will see 10, which is 1 plus 0. Level 1 has 2 redundant. So A1, A1, A2, A2, bit 3, bit 3, bit 4, bit 4. So I have the same mirror or shadow, so that there is like a backup. Okay, so we call this disk mirroring, just like a mirror of the data. So I have 2 of them at the same time. So this has good fault tolerance, because if one failed, the other one is there. Actually, most places, when they want to have high availability, then they will have copies redundancy. You should always have redundancy if you have to have very less, how do you call it, downtime. All right, so this has at least 2 drives, 2 or 4 or 6, so that it's redundant. Then we have level, okay, advantage of this is read request served by either one of them, whichever has minimum access time. Also backup for all data is there. Disadvantage is cost, because you have to use 2, so it is double the price of 1. But 2 at the advantage of having backup. You always have to pay, invest, because invest for backup. Because you invest, because something goes wrong, you have another copy, then you are saved. Otherwise, you are doomed. Okay, then we have RAID 0 plus 1, sometimes they call it 10, which is 1 plus 0, which means you have both of them. So you have RAID 0 bit on both, split on both cylinders, but then you have 2 of these. So this is redundancy of RAID 0, RAID 0, RAID 0, so it's redundant, so it's both together. So minimum you need 4 drives. Okay, provides high data transfer performance. Now level 2, they say this is obsolete, as we will see in some others. Okay, I think we'll leave it for you to go over. I'll share it with you, inshallah. It writes data 1 bit per strip instead of writing data in blocks of arbitrary size. Okay, now this has additional drives. Okay, 1 bit per cylinder, okay, or 1 bit per disk. Then it has additional drives for error correction. For error correction, you have to use Hamming code, or one of the ways is to use Hamming code, which changes, converts the data using Hamming code into another representation, so that if anything goes wrong, you can use Hamming code to recover, you know, the missing part. Of course, Hamming code to convert back and forth will take time. So Hamming code can be used to reconstruct the data on failed drive. All right. So since one data is written on each drive along with the corresponding Hamming code, all drives have to be synchronized to retrieve data properly. This takes time. It is very slow. But wherever you need high security of data, this needs to be done. But it is not used very everywhere. So it's not suitable for applications with high-speed data access. Right? Then suitable for environment where there is a lot of noise or many disk error occurring. Level 3, we have strips or distributes the data 1 bit at a time across all the data drives. Okay, now this distributes the bits. Also, it has parity check, but this parity is calculated by XORing all the bits. So bit 0 XOR bit 1, bit 2, bit 3, bit 4, bit 5, bit 6, bit 7, all XORed to come up with the parity. All right, you know, XORing 0 plus 1 will give us 1, 1 plus 1 or 0 plus XOR, 0 XOR 0 or 1 XOR 1 gives us 0. If they are the same, gives us 0. If they are different, they will get 1. So this is the parity bit. All right, so failed drive can be reconstructed. Level 3. Okay, even though this is the performance is decreased by the parity computation. Of course, you want to have parity for security. You have to decrease the performance. I mean, I don't understand these guys. They always say disadvantage or, you know, performance decrease. Of course, it has to be decreased because everything will be at the expense of something else. Okay, but again, what was most important is to have the data, the correct data. Level 4 of RAID, which is a redundant array of independent devices. Okay, you call it access array. Okay, so is RAID 0 with parity. RAID 0 with parity. Okay, just like we see here. See, we have this. The data is divided into disks, and then we have the parity disk for this number of bits, the parity. All right, which means you have to use several disks. Okay, so not all applications provide equal sizes of data block. That's the problem, so that you don't have similar data blocks of equal sizes. So varying size data blocks becomes impractical, slowing down performance. Anyway, this one attempt. Then we have level 5. Level 5 is level 4, but the parity is not in one disk, but it is split on other disks. So parity disks spread among the entire array. So we have bit parity, then we have bit parity bit. So these bits, so that the parity bit is in different places. Okay, so this has minimum of 3 drives required with one parity. Okay, minimum of 3 drives or 4 or 5, as many as you want. But again, I'm not sure if this is, or this may be the most popular and powerful RAID configuration. Okay, RAID level 5. All right, there's even a better one, which with 2 parities, 2 independent parities, level 6. Level 6, it has A1, A2, A3, then AP, AQ, 2 parity bits. So these 3 have 1 parity, and all of these 4 has 1 parity bit. So even this is more secure, more sophisticated, more expensive, more slow. Everything else expensive, something else. Okay, so extension of RAID 5, additional fault tolerance by using dual parity. Okay, second set of parity is calculated and written across all the drives. All right, so the perfect solution for mission critical applications, level 6. All right. Okay, now, okay, caching. Cache is the last thing in this set. Okay, oh my God, mashallah, oh my God, 1 hour, mashallah, finished almost. My God, I thought 40 minutes will be enough. Okay, caching, basically, I talked about caching, a place to temporarily, to hold the data temporarily. Disk caching stores data or programs that might need to be soon, that may be needed soon in memory chips to avoid to access the data from the hard drive. I talked about this already. So data is saved in the cache as well as is taken, used by the CPU. Then if the data is needed again, it is already in the cache at the beginning of the hard disk. It does have to go to the hard disk and then rotate and seek, in order to get the data again. So, right? Okay, so memory used for this caching can be either portion of RAM or memory chip located inside the hard drive. I think we have read this earlier. Okay, this also memory is called buffer or hard disk cache. All modern hard drives include a small amount of internal cache. Okay, actually, the more cache, the better, and the higher the price of the hard disk. Okay, this cache contains data that has recently been read. Okay, one risk here, of course, if the data has been modified and written to the cache, the data is not written automatically to the hard disk. It's modified in the cache first, but regularly it is updated in the hard disk. But if the data is in the cache and then the system fails before writing the data to the hard disk physically, the data is lost. That's what there's write back caches, which means it is regularly write to the hard disk before the data is lost, just in case the data can be lost. Okay, guys, I think let's take 2 minutes break before we go to the next one. Inshallah, are you still with me? Let me see how many are still there. How many are still awake? MashaAllah, almost everybody is here. MashaAllah, okay, I think Hadil is always there, MashaAllah. Sarah, okay, all these guys are, everybody is good, but some are gooder, meaning they have more time to pay attention, I would say. Everybody has their own sets of circumstances. So when I say something good, means the one who replies to me, I think, faster is the one that well, you get it. I don't have to say it out loud. Okay, so which means please, everybody has to be paying attention. Okay, I'm waiting for somebody to come. Yes. Okay, 1 second, please. Give me 2 minutes. Okay, assalamu alaikum warahmatullahi wabarakatuh. I'm back. Okay, got the thing. Now the summary, I mentioned about the summary earlier. This summary is very important. Oh, I didn't highlight it. You guys, please read the summary and make sure you highlight the important parts. It will help you quickly recognize the important parts, all right? Okay, let's move to the next chapter, chapter 5, input and output technologies, how to deal with input-output devices, okay, technology. Now, of course, the computer, it's not only dealing with the keyboard and monitor, or sometimes or monitor, we have to deal with external devices. For instance, deal with the printer, with the scanner, or with actuators. You know, you want to control something, you want to read data from outside. So you have to exchange data. Sometimes you communicate with another computer, another device, another like large storage device, even the hard disk, some external hard disk. All right. So there is what we have to what is called I/O module, input/output module. These modules, they make communication easy between the CPU and the external devices. So we have to have an efficient mode of communication. Okay, so we have what we call peripheral device. Peripheral means something at the periphery, means on the side, outside, at the periphery. So peripheral device means all the devices that can be connected to the computer. Okay, that can be added to the computer, but they are not inside the computer. So we look at this I/O structure and hardware, peripheral devices, input-output modules, input-output control techniques, input-output interface, and subsystem services, and summary. Okay. Guys, are you still with me? Or you went for 2-minute break and never came back? Never came back. Yes, mashallah. Okay, good, good. Okay, are you listening only or listening and watching? That's a good point. Listening, okay. Some people can understand by listening. I know some people are some people are auditory. Some people are visual. Visual means, I know some people, I had my friend who is a doctor, medical doctor. He memorizes Quran without moving his mouth, just with his eyes. For me, I think it's both. Yeah. Some people, no, they like to hear. For instance, children, we used to repeat, recite Quran for the children, especially their mothers, and then they repeat, or they just recite to them, and then they learn by hearing. So hearing and seeing is the better way. Of course, the better than hearing and seeing, and also doing, meaning reading out loud, rephrasing, explaining, taking notes, which we should be doing in order to learn. Okay, so learning outcome, we define all of these things and be able to explain, differentiate between them. Okay, some terminology as usual. We have the DMA, direct memory access. DMA is basically DMA device or chip is some module, okay, or chip actually, 8237, the first one that was used by IBM PC. That direct memory access, which it means it helps the CPU deal with the memory. Okay. It lets the DMA take care of dealing with data between the memory and external devices, like reading data. Because when CPU wants to read data from outside, from external device, it has to read it and save in the memory. When it wants to send data to the external device, it has to take it from the memory where it is working on, then send it to the external device. So dealing between this memory and I/O device, the DMA comes in between. So DMA, direct memory access, takes charge of exchange of data between main memory and I/O module. Still, we have an I/O module because it deals with external devices, different devices. The I/O module is also another step in between. So 8237 DMA controller, that is the chip. I think I have it here. No. Okay, you can just look for 8237 DMA application note. Application note, and you get the PDF file. Just go through it. This is the older one. Then it will do, we have error detection code that which, each character or signal conforms will have the CFS, frame check sequence or checksum. This is error detection code. That is just like we have seen for the parity, it's done by XORing the bits. So at the end we have 1 bit. This frame check sequence will XOR, or in a way, all the bytes, all the characters that have been transmitted or received both ways with the frame check sequence, and then compare. Is it the same, meaning everything is okay? Is it different, meaning the data that has arrived is not correct? So this is for error detection. Error detection. Correction, need to use some kind like Hamming code and some other specialized codes. At least for correction, we use retransmit. Okay, retransmit. We do not acknowledge, or you acknowledge receiving only limited number, then whatever was not received will be transmitted again. Okay, so here, the first, okay, input, output, I/O, movement of data between computer or CPU and the peripheral devices, input devices and output devices. Now, interrupt-driven I/O. Interrupt-driven I/O. Now, what is interrupt? Just now I had an interrupt. I was here, somebody came at the door, so he interrupted me because I was expecting him actually. But suppose I'm just talking, someone comes there and then he knocks at the door. That is an interruption. So I can either entertain this interrupt, so I can put you guys on hold, save what I have been doing, then look at or entertain this interrupting device. I acknowledge, and then I say, what do you want? Then I provide the service needed. Then I come back and load, restore, recover, restore basically the where I was and continue from there. So this is using interrupt. Interrupt means the CPU will not be always paying attention to the I/O, waiting for it to finish. No, it will tell the I/O device to do something once, or when it needs service, it will request from CPU to interrupt the CPU. So the CPU will be looking for interrupt every time it finishes an instruction sequence. Or once the service is done or completed, then it will interrupt and say done, finished, and then the CPU will look at that, entertain, do whatever needs to be done, when the interrupt arrives. Different devices can have different interrupts, so have different CPU can have one interrupt for many devices, so they can select which or search which device is the interrupting device, or it can be different interrupts. Each interrupt service serves a certain device. So interrupt is a form of CPU issues an I/O command, then CPU continues to execute whatever it has been doing until that I/O device finishes. Then it will enter saying, I have finished, or I'm done, I'm ready to provide the data, or I have received the data. Then CPU will not be bothered with it all the time, only when it is done or finished executing. So CPU will continue to execute subsequent instructions. The interrupted, it is interrupted by I/O module when it is completed, when it has completed the work. So CPU will not, because we have the I/O, sometimes CPU will want to write to the I/O. This is the primitive types. Basically, this can be done with microcontroller because it doesn't have a lot to do. It's a specific task. It will want to write. I wait for the I/O device to finish. It will wait for it. CPU normally doesn't have to wait for it. It will say, okay, do this, and when finished, let me know. CPU could go and continue doing its, other things, other tasks that it is supposed to be doing. Then, when the other device, when the I/O device is done, it will send the interrupt signal to the CPU. CPU will be watching every now and then. Then, of course, it has to do. Then it will see, oh, interrupt is there. Okay, then it will say whatever it's doing. Service interrupt, okay, thank you very much, okay, and then check whatever that was to do, and then when that service routine for the interrupt called interrupt service routine, ISR, when it is finished, the CPU will then restore whatever it has been doing, because it will save the program counter, the status, what it was doing, all the registered values on the stack, usually. Then it will restore them, retrieve them back, bring the situation back where it was before the interrupt arrived. I/O channel, input output channel. This is a dedicated okay, channel to deal with the I/O device basically or module, release the CPU of details of I/O operation, executes a sequence of I/O commands from main memory without the CPU intervention. Okay, so this is a dedicated channel or device actually. I/O module is a module that is between the CPU and the I/O devices, all right? So it's one of the major component types of the computer. Components within the computer, it is responsible for control of one or more peripherals and for exchange of data between the peripheral and the memory and CPU registers. Right, so CPU will have to go through this module to transfer the data, also to check on the I/O device, whether it is ready, whether it has a problem or whatever. Then we have multiplexer channel, same as that, channel designed to operate with a number of I/O devices simultaneously. Okay, but this is slower. This is dedicated and much faster. Peripheral device is a device, I/O device. Programmed I/O. CPU issues an I/O command, so an I/O module, and must then wait for the operation to be completed before proceeding. It will send the command to the I/O device, I/O module. This is called programmed I/O. We have certain commands that are used for the memory, specified the memory location. Also certain commands that are specified for the certain also location, but they are assigned to peripheral devices. Okay, some have programmed I/O included, like memory address, specifying the particular address of the I/O device as part of the memory space, and some are particular commands that are only for the I/O devices. We have selector channel. This is designed to operate with only one I/O device at a time. Okay. All right. So a lot of things to go over here, but this one you need to read thoroughly. All right. Okay. So CPU needs to be communicated with outside world. Okay. Peripheral device. Okay. Now this. Okay. Let's see here. This is external device. What is external device? Basically a device which deals with the environment. Okay. Data to or from environment. Maybe measuring humidity, measuring speed, measuring temperature, measuring something. Then we have transducer. What is transducer? Transducer is a device that converts energy from one form to another. Basically converts energy from whatever it is, heat, humidity, height, speed, or whatever, into electronic signal. Okay. Then it will save that data in the buffer. Then it has control logic to communicate, to control it. Then it will be connected between the buffer, because what's in the buffer is the data. So data bits to and from the I/O module, it controls this device. Then this control logic also connected to the control signals from the I/O module, and also can give the status. I'm ready, I'm busy, I'm active, I'm waiting, or whatever, according to its design. So this is the device, external device, which measures the phenomenon that we want to measure: heat, speed, height, pressure, whatever it is, temperature, humidity, and then send the data to the I/O module in order for it to be sent to the CPU. Okay. Now, why do we have? Okay, let's see. Peripheral are electromechanical and electromagnetic external devices. Those are the peripheral devices. Some complex, some less complex. Okay, external devices can be classified into these online devices, such as terminal, communicate with the processor in an interactive mode. In terminal can be just like terminal is a keyboard with a screen. All right, it can communicate with the computer. This can be online, can be also offline. For instance, printers. You just send to a printer and forget about it. The printer will take care of handling, the printing process. Then we have real-time data transmission, A to D, D to A, analog to digital conversion, digital to analog conversion, and then storage devices such as tape and disks that can be classified as I/O devices as well. Okay, now terminals, we know the terminal. We talked about terminal previously. Okay, keyboards, you know all about the keyboards. If you don't, you are in big trouble. Anybody doesn't know what the keyboard is? Okay, and how it works. We talked about that. ASCII. Mouse. Okay. Some mice are nice. Okay. Some mouses. Is it mouses or mice? The plural of this mouse. This is HP. Okay, so this is okay. Mice, you know how the mouse works. All right, I'm using wired mouse, which is serial. Then you have probably the Wi-Fi mouse using the Wi-Fi signal, wireless fidelity, okay, using electromagnetic signal. We have the printers, daisy wheel and dot matrix. I think we talked about this last time. The printers, this is not our point here, okay? Printers, what they consist of. I think we talked about printers. Okay, daisy wheel basically similar as the typewriter, where you just press, you know, hard with it, so the proper letter will come in front of the ribbon, which will be hit, and then the ink or the shade of darkness will appear on the paper behind. Daisy wheel. Also dot matrix, basically like dots in an arrangement, like rectangular arrangement, where certain pins of these dots will be activated to again push the ribbon, print on the paper. Then we have the inkjet printer, which splash ink of 3 colors, CYM, cyan, yellow, magenta for the printer, not RGB. RGB is for the monitor. Even though they are similar, but they're the opposite. Okay, CYM are the opposite of RGB. Okay, we talk about this in the multimedia technology class, inshallah. So this spray ionized ink on the paper. Then we have the laser printer, which uses electrostatic discharge, okay, from the high voltage drum for the data, for the toner to be attracted to the drum, and then it will be printed on the paper, moved to the paper using the corona wire, high voltage wire. We read about laser printer. Okay, I work for a company where we were the dealer for laser printers. I was in charge of printer maintenance long time ago, in 1980 something. Okay, magnetic disk. Magnetic disks are the hard disks. We talked about them at length earlier today. Okay, now we have input-output module. This is our point. Okay, why do we need I/O module? Because of different speed of data transfer, different forms of data to be transmitted. Then also data transfer rate can be slower than CPU and RAM. Sometimes some devices are slow, so they need somebody in between so that they can do the adjustment of the transmission of the data. Some peripheral data transfer rate is faster than that of the memory or processor. I thought, you know, this is not true, but it is true. For instance, some outside memory, they go, okay, the memory usually, okay, DDR4, I think I have in my laptop, DDR4, 1.6 gigabit per second. We had DDR5 up to 100 gigabyte per second. The memory speed, the data transfer speed of the memory. Okay, now, okay, here in sequential streaming, I found this from ChatGPT. Sequential streaming, the peripheral SSD, external SSD, high speed, okay, high speed data transfer, it has. High speed network cards also can go up to 200 gigabit per second. Also the GPU, which is now the successor of the arithmetic. We have the CPU and the CPU and the other used to be called, we have CPU and arithmetic coprocessor. We had 8088 and 8087. That is the math coprocessor. This is the graphics processor unit, which is basically number crunching, mathematical, optimized CPU, okay, in the GPU. Now the GPU contains that CPU or graphic CPU with memory, with some other, they can work at the speed of 3 terabyte per second. 3 terabytes per second. This is the heart of the AI chatbots that we have now. Okay, so these can be very, very, very quick. So we have to have somebody to adjust the speed between the CPU and memory and the external device. So we have the I/O module. I/O module connects to the CPU on one side, to the control lines, to data lines and address lines or bus, and to the other peripherals on the other side. So this between the CPU and other peripheral devices. All right. Now, so it interfaces between them. Interface is the intermediate device. Now, main functions of the I/O module: controlling and timing, to coordinate the flow of data. Okay. Processor asks the I/O module to check the status of the device. I/O module will return the status. So I/O module will ask the device for its status, just as we have seen, and the I/O device external will send the status back to the I/O module, and the I/O module will send it back to the CPU so that the CPU can then request for data transfer to the I/O module if the device is ready, and then I/O module gathers the data from the CPU and transfer it to the I/O device, or if it wants to read from I/O module, it will read the data and then transfer it to the CPU registers, or to the memory, okay, or to put on the data bus. Actually, the data will be on the data bus, and then the CPU can command the memory to take this data in. So this I/O module also will do communication with processor involving command decoding. CPU will make the command, it will decode the command. Also, it will involve the data taken from the CPU, status reporting, both ways, fetching and reporting, and address recognition, address that is coming from the CPU. Also, device communication involves sending the command, translating the command to action to be done by the I/O external device, status information requesting from the I/O device, and data whether receiving or sending to the I/O device. Also, data buffering will save the data so the I/O device can take it at its acceptable rate. All right, so the CPU doesn't have to wait. We have, usually even for the memory previously, when the memory was not very fast, we used to have zero wait time, or they call it zero wait time. There was a term for it. Anyway, so the CPU would have to wait 1 cycle, 2 cycles, 3 cycles for the memory to get the data. Now, no more. Everything is very fast. But our external devices can be slow, so that data will be taken by the I/O device, hold it until the I/O device can take it from the I/O module, and the CPU doesn't have to worry about that. So I/O module must be able to operate at both device and memory speeds. Okay, so it can increase or decrease speed according to both of them. Also, it is used for error detection. So if there's any mechanical or electrical malfunction reported by the device, then the I/O module can report it to the CPU. For instance, paper jam. We always have this paper jam, out of paper, bad disk track. Okay, so the CPU will have an error message coming, then it will try to do whatever needs to be done and detect transition error. Okay, so this is I/O module. So this is the data lines, address line, control lines from the CPU side. Okay, so interface to the system bus, which connected to the CPU, and then connects to external device interface logic. So this one device, another device, and other devices. So it has control lines with that device. It has the status line and data back and forth. Control means start, stop, whatever. Then status, okay, what is your status? It will give the status, ready, not ready. Okay, and that can be sent or received from the I/O device. Then we have the input-output logic, which is control coming from the CPU with address line specifying, address line specified which device of these to be accessed. Also, we have the data lines, okay, to tell data is ready, take the data is not ready, and so forth. Okay, So input-output control techniques, we have several techniques for input-output control. We have programmed I/O. Okay, in brief, okay, I think I'll probably come back to this, but let's go to this flowchart. 3 techniques for input of a block of data. Now, this is programmed I/O. The CPU will issue the program to the I/O module to say, okay, I want to read. Okay, so issue command to the I/O module. CPU wants to read. Then it will read the status of I/O module. I/O module will send the status to the CPU. If it is check the status not ready, continue checking the status. See, if there is an error, it will report an error condition. If the status is ready, then it will read word from I/O module. Read 1 word. So I/O module will send the word to the CPU. Then, or write word. Okay, yes. To CPU. Then CPU will want to write the word into memory. So CPU will write into memory and then done. No, not yet. Then go for the next byte. So this happens. So it means the CPU will be busy, you know, sending every byte at a time, 1 byte at a time, busy with it all the time, and waiting for the I/O device to be ready to say, okay, received, and so forth. So this is I/O, programmed I/O. Now, 4 types of I/O commands: control to activate or deactivate, test, check the status, read or write. Read data from memory to the I/O, read data from input device into the memory, or write data to the output device. We call it I/O, input output. All right? Then to the peripheral. Now, I/O interaction, process fetches from memory are mapped in I/O. Map meaning every device has a particular address. So when the address is specified by the CPU, it means that particular device is the one that is meant for this interaction. All right? So we have I/O commands specific for I/O. Also, they can be from like memory address, read from memory, but the address will be assigned to the I/O device, so it will be the I/O device that is intended. Okay, I/O commands that process issues to an I/O module to execute the instructions. Many devices connected through I/O modules to the system. Each device has a unique address. Okay, so processor will issue the I/O command. Command contains the address of the required device. When the processor, main memory, and I/O share the common bus, 2 modes of addressing are there. Okay, when there's common bus, two modes of addressing. Okay, we have memory mapped I/O, which means the single address space for memory locations and I/O devices, meaning a memory address but allocated to the I/O device, but within the memory space. Or we have isolated I/O. We have specific addresses for the I/O. This memory organization for the device. Okay, the isolated for the address space of memory, isolated from address space of memory. So they are only, so they can be within the memory, but in your connections, and we do this in microprocessor system design, you know, we don't do it here. The address will itself will cause the decoding or the selection of which I/O device to be activated for reply using this address. Okay, so this is I/O isolated. Special commands for I/O also. Some commands are the same for the memory and for this memory map, and some commands are specific for I/O depending on the microprocessor architecture. Okay, so CPU will want to read in a block of data, for instance, there, byte by byte, or 1 word at a time, 16 bits at a time. Okay, 1 word, which is double byte. For each word, it is read in. The process must remain in status checking. Check, are you ready? Give me 1 byte. Are you ready? Give me 1 byte. So until it determines that the word is available. Okay, all right. Then the module data in the data module data register, meaning here to check the status, read the status. If not ready, continue checking the status. When it is ready, then it will read the data. All right. Okay, so that is programmed I/O. Then we have interrupt-driven I/O. Interrupt-driven, okay, works this way. The CPU will send to the I/O device and say, I want to read from the I/O module. And it will specify the address of the particular I/O device to read from. So if it's one I/O module with many devices, the address itself will specify which device is intended. Okay, so CPU will issue the command to the I/O module, then it will go and continue doing other things. All right. So when the I/O module is ready with the data, it will send an interrupt signal to the CPU, basically one line called the interrupt signal, telling the CPU that I am ready. Interrupt meaning data is ready. Then so the I/O module will send to the CPU the interrupt. Okay. Then the CPU will check status. If it is ready, then it will read from the I/O module, read the data. So when it receives the interrupt, it will check status ready. Then data will be written to the CPU, and the CPU will write the word to the memory. And if it is done, fine. Otherwise, it will go to issue the next one, read the next word. Okay, word means double byte. Usually word is double byte. Read the next word, and then CPU will go on its business until it is interrupted that, okay, data is ready. Data is ready. Yes, okay, give the data to the CPU. CPU send the data to the memory and continue. So this is interrupt. The idea here is CPU will just issue the command and will not be just waiting for the I/O I/O module to get the data. No, it will do its own work until the I/O module gets the data from the I/O device, have it ready, interrupt the CPU, say, I am ready. The CPU will double check, are you ready? Okay, then it will take the data. So this is even better because it relieves the CPU from having to wait on the I/O device. Okay, so it doesn't have to be waiting. So processor will issue the I/O command to the module and then go on to do some other useful work. I/O module will then interrupt the processor to request service when it is ready for data exchange with the processor. Processor then execute the data transfer, then resume its former processing. Okay, continue processing. Basically, when the CPU attends to the interrupt, it will save everything it is doing. Save the program counter, which instruction it is pointed to, so that it will be fetched next. To save the content of the register it is dealing with, and save the CPU status, which means the result of the last instruction that was executed. Its status all will be saved on the stack. Then CPU will entertain the interrupt. Look at the interrupt. Which interrupt is this? Then it will fetch the interrupt service routine location. Then go to that location, get the instructions, implement them, service the interrupting device, and then when done, it will go back and retrieve its CPU status, we call it, which is the program counter, the status of the last instruction. CPU after the last instruction was executed, and the content of the registers back and continue from where it was interrupted. So this is all explained in these paragraphs. All right. I think page 12. Okay, let's see if we can go over this. So detail here. The role of I/O module. Okay. For input, I/O module will receive read command. For output, it will receive write command. I/O module will read data from the peripheral device. The data will be put in the buffer in the I/O module. Then I/O module will send the interrupt to the processor over the control line. Module will wait until the data are requested by the processor. Then the request is made. When the request is made, the module will place the data on the data bus so it can be ready for another I/O operation. Then this is the I/O module. CPU for the input issues the read command, then goes off and do something else. At the end of each instruction cycle, the processor will check for interrupts quickly. When the interrupt arrives, then processor will save the information about the current program, which is CPU status, like program counter, processor registers, and process the interrupt basically process the interrupt service routine which is assigned to this interrupt. In this case, it will read the word of data from the I/O module and store it in the memory. Then it will restore the information, the CPU status of the program it was just working on, and resume execution. Okay, this we have seen that in the flowchart. Sometimes there are multiple interrupts, multiple I/O modules. So there are 4 techniques to identify which module is the interrupting one. Sometimes we have multiple interrupt lines, so it knows which line has, interrupt was issued on it. Sometimes there is one interrupt and several devices connected to it. So we do software poll. Poll means read one at a time. Process will ask each module in turn to determine which module caused the interrupt. Okay, this is time consuming. Then there is daisy chain. The CPU will just send the acknowledgement, which is called hardware poll. All I/O modules will share a common interrupt line. So the interrupt acknowledge line sent by the CPU to all these devices. When it reaches first one, second, third, the device that reaches the acknowledgement, the device that has been the one supposed to do the action, will send the address of the interrupt service routine. Okay, so when process senses interrupt, it will send interrupt acknowledge. Signal propagates to I/O modules until it gets to the requesting module, places the vector, which is address of the interrupt service routine. Okay, for that module to do the action, to put the address on the bus, data bus. SEP will take that address from the data bus, then use it on the address bus to fetch the handler routine or interrupt service routine. Then there is bus arbitration. Basically, the module will first claim, the bus will say bus request. So CPU will say, okay, bus granted. Okay, before it does the interrupt, it will request to claim the bus. The only one module can raise this line at a time. Processor detects the interrupt, then responds to the interrupt acknowledge line. The requesting module places its vector on the data lines. This vector is the address of the interrupt service routine. Okay, so that CPU knows which instructions to execute to serve this interrupting device according to the request that it has made. Okay, so now then we have the direct memory access. Direct memory access is the best of all worlds. Direct memory access is when you want to transfer many blocks of data, not only a few bytes. So here in the flowchart, we have the direct memory access. The CPU will issue a read block command to I/O module. So CPU will tell the DMA, okay, I want to read a block command. So the DMA will take care of communicating with the I/O module and getting that data and interrupt the CPU when the data is ready. Read status of DMA module. Okay, so the CPU will read data, the status of DMA module. DMA module says I'm ready. Then okay, after it interrupts the CPU, okay, the DMA will interrupt the CPU. CPU will read the status of the DMA, and then it will relinquish, give the control of the memory data lines or the data bus to the DMA, so that DMA can do direct memory access. It will access the memory directly and store, because CPU wants to read. It will store the data that is read from the external device, maybe a hard disk, into the memory. So the CPU will not bother by sending the data to the memory. The DMA will do it. So the CPU is just like the king, send the command, what memory locations to read from, or what data to read and save it to what locations, send it to the DMA. The DMA will do the rest. So the DMA in this case will be the deputy CPU as far as data reading and storing into memory is concerned. So this is called direct memory access. It relieves the CPU from having to bother about memory exchange, memory data exchange. That's why it is called direct memory access. Direct memory access. Okay, So now direct memory access, where we, okay, so here, when a large volume of data is to be moved, DMA technique is used. During DMA transfer, the CPU is not used, okay, and has, okay, CPU doesn't use, okay, let's see. During the transfer, okay, CPU is not meaning the DMA, when it does the transfer, it doesn't involve the CPU, all right? It's not, it doesn't involve the CPU. It has, CPU has no control on the memory bus because it relinquishes the control of the memory bus or data bus to the DMA. DMA controller takes over the buses to manage the transfer directly between IO device and the memory. All right. So data, the DMA will have full authority to transfer the data. This authority given by the CPU. Now, DMA module, then figure 5.5. This 5.5. DMA block diagram. This is a DMA block diagram. What does it do? So here, communicates with the data lines, address lines of the system, and takes control signals from the CPU. Read signal from the CPU, it has control logic, address register, data register, and data account. So it receives the read signal from the CPU or write signal from the CPU, assuming the CPU wants to read or CPU wants to write. Then it will send interrupt when it has done this operation. CPU will be requesting the DMA, so DMA request will be sent from the CPU to the DMA. DMA will send DMA acknowledge that, okay, request acknowledge, okay, I will take care of it, and when it finishes taking care of it, it will send the interrupt saying, I have done the operation. DMA will receive the address line specifying the data to read from and to save to in the memory, at which address. Also, data lines will be available for the, and then also the data count, how many bytes of data need to be read or written. This all will be sent to a DMA, and the DMA will have full authority to act on this command. Okay, this is the quite, actually it is not difficult, it's sensible, it makes a lot of sense. So when DMA module takes control of the bus, it communicates directly with the memory. DMA transfers a block sequence consisting of a number of memory words transferred in a continuous, fast way, while DMA controller is master of the memory bus. CPU will relinquish. In that case, CPU, even though it's connected to a data bus, but it will have the data lines as high impedance or in tri-state, so that it doesn't affect or get affected by the data bus during this time. Okay, so this mode of transfer is needed for fast devices such as magnetic disks, where data transmission cannot be stopped or slowed down until the entire block is transferred. Okay. Alternatively, we have what is called cycle stealing, which allows DMA controller to transfer one data word at a time. It requests data bus from the CPU, CPU will grant, send one word, finish. Then request second one, granted, send. Request use the bus third time, granted, send the word. Okay, so afterwards, it must return the control of the bus to the CPU. This is called data or cycle stealing. Cycle stealing. Okay, so CPU delays its operation during that time when the DMA steals the cycle or request actually for one memory cycle, so that to allow direct memory IO transfer, okay, to steal one memory cycle, to send the data to the memory. Okay, cycle stealing technique is more common. All right, so DMA technique is to read in a block of data from peripheral device into memory. This is figure 5.4c, 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 what is it? This is 5.6, 5.5, what is 5.4c? Oh, okay, we have seen that already, all right? Okay, a lot of, this is what you have to do, guys. You need to read this and go back and forth, all right? You need to read this, read it out loud, visualize, take notes of it, see what is happening. DMA, we were here. 54C, okay. DMA mechanism can be configured in a variety of ways. All right. Here, okay, we have 54A. Okay, here we have one same bus line, a single bus, right? Where the DMA is connected, IO is connected. So here, the DMA will have to request the data from the IO. I will send the data to the DMA over the data bus, so that uses it once and interrupts the CPU. Then the DMA will want to write to the memory, and the second time it will suspend the CPU connection with the data bus. Okay, so for each transfer use of the bus, the data, the CPU will be suspended, meaning CPU will be suspended, will not have access to the data bus. DMA will take the data once from the input-output device, so it uses the data bus. CPU is isolated from it. Then DMA will want to write to the memory. Then the data bus will also be used by the DMA, and CPU will be isolated from it. Okay, this is using common or single bus. Sometimes the IO units are connected directly to the DMA. So I have single bus, but integrated DMA with IO. So the DMA will get the data from the input-output devices, not bothering the system data bus. Only bother the system data bus requested from the CPU when it wants to write to the memory, or when it wants to read from the memory according to the command from processor, and in order to send to the IO. So this will be only once, disturbing the connection between the CPU and the data bus. All right. Then we have also, again, DMA connected to the bus to different IO devices. And again, it will read from IO devices without disturbing the system bus. Then when it wants to write to the memory or read from the memory, it will disturb the connection between CPU and the memory, the data bus that connects them. So there are many applications that use DMA transfer for fast transfer to magnetic disk and memory. Also to update a display, this monitor is refreshed about 63,000 times, the frequency of refresh every second. So this refresh is taken care of by the DMA. CPU doesn't have to worry about that. Okay, in an interactive terminal. Okay, so image on screen display is kept in the memory. Of course, every pixel in the memory has its logical value in the memory. Every pixel on the screen has its value in the memory, so that system will read from the memory and write into the screen. Okay, then finally we have the dedicated channel, IO channel. We have dedicated devices with their own CPU. Okay, with dedicated channel to communicate with fast device. Okay, which is like in this case. Okay, selected channel, dedicated channel to connect to the IO very quickly upon request from the CPU, the control from the CPU. Then we have the selected channel with many more devices, where it will multiplex, take them one at a time, or it will slice the time between them because they are slow, so it can accommodate that. But this one dedicated for a very fast IO device. All right, so you need to read this. I have also had it, the selected channel for multiple high-speed devices. Okay, multiplexer is for slower devices. Here I have some write-up. Okay, selected channel is designed for high-speed devices, but it handles only one device at a time. Channel selects one device, then dedicates the entire channel bandwidth to a single device until the transfer is complete. Okay, the multiplexer channel, I think, make it bigger. Oh, it's very confusing there. Multiplexer channel design, yeah, I think, for many slower devices, and it can handle several concurrent IO operations at once. The channel time slices, gives a slice of time, part of a second, part of a millisecond of its bandwidth among many devices. This gives attention, it gives attention to a device only when it needs service. Keyboard input printer. All right. So this is the selector channel. Of course, for high-speed peripherals such as tape and disk, these are used. Then we have application I/O subsystem services. This is taken from the NT input-output subsystem. NT is the Windows NT, NTFS, file system. So NT is the new technology. All right. I/O subsystem. This is part of the operating system. It's a framework which contains all kernel mode drivers. Kernel mode, how the operating system is application or user mode and kernel mode. User mode is the one that deals with the user. Kernel mode is the one that deals with the devices or peripheral devices or other devices of the system. So kernel mode drivers, we call them drivers, because drivers means the software that deals or firmware that deals with the hardware, okay, controlling and interfacing with peripheral devices. This subsystem composed of the following components: NTIO manager, file system drivers, because file system deals with the hard disk, okay, local disk-based file system, network redirectors, network file servers, intermediate drivers, device drivers, filter drivers. All of these are kernel mode drivers, basically, usually in written, of course, transmitted, transformed into machine language, because they deal with the I/O devices in electronics, in signals. Okay, so all of these components are part of the NTIO system. Now, the NTIO manager functions, the first one, okay, manager functions are many, defines and supports the framework that allows operating system to use peripherals connected to the system. It provides a set of generic system services used by various subsystems to actually perform I/O or request other services from kernel mode drivers. So we don't have to worry about all the details here. Then it also defines a single I/O model where all drivers will have to conform to, so that they all work in, harmony. This model consists of objects and set of associated model methods used to manipulate the objects. All right. Then it will support the implementation of the installable file system that use the peripheral device and connect to the system. It supports dynamically loadable kernel mode drivers, provides support for device independent services that can be utilized by other components. It can interact with the NT cache. Remember, cache, temporary data storage manager, to support virtual block caching to file data, and interacts with the NT virtual memory manager and the file system implementations to support memory map files. Okay, this is quite involved here. Actually, this is only top level. It can be very sticky wiki. Anyway, just some idea. And this summary is a very good summary that explains in brief whatever has been covered in this whole lecture material. It's very good. Please go through it. Make sure this even makes you understand more. When you read the details, you hear the details now and then, you might got all of this stuff confusing. You read the summary, then you start to see through the maze of the information there. Okay, so the summary always summarizes, makes recaps the most important points about the item or the thing, so that's easy. It's easier to understand. This NTIO manager details, you don't need to worry about it. You just need to know the basic idea. Okay, guys, thank you very much for those who stayed with me. MashaAllah, I see some of you already still there. Thank you very much. I appreciate you staying until now. So this is the end of chapter 5, sorry. Next time we start chapter 6 and 7. After that will be chapter 8. I will send you all these chapters, inshallah, from today. If I don't, please remind me. I have to rush after this, actually, but remind me to send you all the chapters from 4, 5, 6, 7, and 8, inshallah. Thank you very much. All the very best. Good luck with the quiz, inshallah, and the assignment. Wish you all the very best. Stay safe and healthy. Wassalamu alaikum wa rahmatullahi wa barakatuh.